So today we're doing one of our deep dives, getting into the continental crust, the foundation for all the land masses.
That's right. We've got some really interesting geological notes here.
Yeah, and the mission, as always, is to sort of pull out the key stuff, the fascinating bits about it, give everyone a shortcut to understanding this, fundamental part of our planet.
Exactly. Think of it like uncovering a story maybe 4 billion years in the making, etched right into the ground.
4 billion. Okay, so we'll look at what its thickness, what it's made of.
Yeah. Thickness, composition, how old it is,
Yeah.
how it even formed, from, how thick it gets under mountains to the tiny minerals that make it up.
Okay, let's kick off with size then. Thickness. How thick are we talking generally for continental crust?
Well, on average, you're looking at somewhere between, say, 30 and 50 kilometers deep.
30 to 50 kilometers. That's already pretty substantial. Hard to picture, really.
It is, but that's just the average.
Right, because I remember reading it gets, a lot thicker in some spots.
Oh, definitely. The really dramatic increases happen under big mountain ranges. Think about the Himalayas.
Yeah. How deep does it go there?
Under the Himalayas, the crust can plunge down over 70 kilometers.
70.
Geologists actually call it a mountain root, like this massive bulge of crust pushing downwards, basically holding up the mountains above.
A mountain root. That paints quite a picture. It really shows the scale of those forces.
It really does.
And I guess it's the opposite elsewhere, like near the coasts.
Exactly. As you move toward the edges of the continents, toward the oceans, the crust thins out quite a bit.
Okay, so hugely variable in thickness. Now, what about what it's actually made of? What are the main building blocks?
The main rock type is what geologists call felsic rock. Granite is the classic example everyone knows.
Granite? Okay. Light-colored stuff.
Generally, yeah. Felsic rocks are rich in silica and aluminum. Actually, that's a handy term sometimes used. Seal.
Seal, S-I-A-L.
Yep. For silica and aluminium. Just a quick way to remember the main components.
Seal, got it. Good mnemonic. So mostly granite-like rocks, but our notes mention others too.
Oh, yeah. It's not just granite. You also find sedimentary rocks, sandstone, shale, formed from accumulated sediments, and metamorphic rocks, too. Rocks that have been changed by heat and pressure deep down.
Okay.
But if you looked at the whole crust, the sort of bulk composition, it averages out as broadly granitic, or what we call intermediate, around 60.6% silica by weight.
Interesting. 60% silica. And is that composition the same all the way down, top to bottom?
Not quite. There's a definite change as you go deeper. The upper crust tends to be more felsic, chemically similar to maybe dacite, which is a volcanic rock.
Okay, more felsic on top.
But as you go down into the lower crust, it gets more mafic, more like basalt, which is denser and darker.
So it's kind of layered, chemically speaking?
You could think of it that way, yeah. A sort of vertical gradient.
A layered cake of rock. I like it. And what about the specific minerals making up this cake? What are the most common ones?
Okay, by weight, the big one is feldspar. That makes up about 41% or so.
41% feldspar. Wow.
Then comes quartz at around 12%. And after that, pyroxenes, making up roughly 11%. Those are the main players.
Feldspars, quartz, pyroxenes. Right. Now, the notes also mention something called incompatible elements. Sounds intriguing. What's their deal? Why are they special here?
Yeah, the incompatible elements.
Yeah.
This is where the geochemical fingerprint of continental crust really stands out.
Fingerprint? How so?
Well, continental crust is significantly enriched in these elements. We're talking things like rubidium, uranium, thorium, potassium, the light rare earth elements.
Okay.
Compared to oceanic crust, and especially compared to the mantle underneath, there's just a lot more of this stuff concentrated in the continents.
And why is that concentration significant? What does it tell us?
It tells us that continental crust isn't just simple mantle melt. It has this long, complex history. It's been through processes of melting, differentiation, reprocessing over billions of years. It hasn't been recycled as quickly as oceanic crust. So it kind of collects these incompatible elements that don't easily fit into the crystal structures of mantle minerals.
Okay. So it's like a unique chemical archive because it's stuck around for so long.
Exactly. A very ancient, chemically distinct archive.
Which leads us nicely to another key property, density. How does continental crust stack up density-wise?
Well, the key thing is that it's less dense than the layers below it. Less dense than oceanic crust and less dense than the mantle.
Okay. Less dense. Do we have an average number?
The average density is about 2.7 grams per cubic centimeter.
2.7 GC until.
Got it. And like the composition, does the density change with depth too? It does, yeah. It increases as you go deeper. Starts around maybe 2.66 GCM under the surface and gets up to about 3.1 GCM down near the base.
Why the increase? Just pressure.
Pressure is a big part of it, yeah.
Yeah.
But also that shift towards more denser minerals in the lower crust plays a role too.
Right, the basalt-like stuff. Now, this lower overall density, 2.7 compared to denser stuff below.
Yeah.
That reminds me of why continents, why they stand high. Is that related?
That's exactly it. It comes down to a principle called isostasy.
Isostasy, okay.
Because continental crust is less dense, lighter, it essentially floats higher on the denser, more fluid mantle beneath it.
Like an iceberg or wood on water.
Precisely. A very similar idea. Wood flows higher than, say, a dense rock would in water. Continents float higher on the mantle. That buoyancy is the fundamental reason we have high-standing continents and low-lying ocean basins, which are floored by denser oceanic crust.
That floating continent idea really makes sense. A fundamental balance based on density. Cool. Okay, let's shift gears to age. The notes stress that continental crust is generally really old.
Yeah, that's one of its defining features. It's typically much older than oceanic crust.
Why is oceanic crust younger?
Because oceanic crust is constantly being created at mid-ocean ridges and then destroyed, recycled back into the mantle at subduction zones. It doesn't hang around nearly as long.
Ah, okay. So continental crust just persists.
Pretty much. It gets deformed, eroded, added to, but large parts of it are incredibly ancient. It contains some of the very oldest rocks known on Earth.
Seriously, like how old are we talking? Give us some perspective.
We're talking billions of years. Billions with a B. But Nose mentioned a specific example, the Acasta gneiss.
Acasta gneiss. Where's that?
It's found up in Canada and dates back over, wait for it, 4 billion years.
4 billion? That's almost unbelievable. Almost as old as the Earth itself.
Pretty close.
Yeah.
It really gives you a sense of deep time, doesn't it? Thinking that bits of crust that old are still around today.
It absolutely does. So how did this incredibly ancient stuff form in the first place? What's the process?
The main engine for creating new continental crust is those subduction zones we mentioned, where an oceanic plate dives down beneath another plate, often a continental one.
Okay, the diving plate. What happens then?
As the oceanic plate sinks, it heats up and releases water and other fluids. This triggers melting in the wedge of mantle rock sitting above the sinking plate.
Right.
And that magma, is less dense, so it rises.
Towards the surface.
Exactly. Some erupts as volcanoes on the continent, forming mountain ranges like the Andes, for example. Other magma cools and solidifies underground, adding to the bulk of the crust. It's called granitoid rock, basically.
So subduction zones are like crust factories.
In a way, yes, major factories. But that's not the only way continents grow.
Oh. What else contributes?
Well, continents can also grow sideways through accretion.
Accretion, like
Yeah.
adding stuff on.
Yeah. Material can literally get scraped off the top of the subducting oceanic plate and plastered onto the edge of the continent, like piling snow in front of a plow.
Okay, scraped off bits. What else?
Also, continued volcanic activity along the edge of the continent, those volcanic arcs, keeps adding material. And sometimes whole chunks of crust, like oceanic island arcs.
Like Japan, maybe? Or parts of it?
Sort of like that, yeah, or ancient versions of them. These can collide with the continent and just get stuck there, welded on.
So continents are kind of like collages, patchworks.
That's a great way to put it, especially the process called terrain accretion. Terrains are these distinct crustal blocks. Could be old island arcs, could be microcontinents that travel across the oceans on tectonic plates and eventually bump into and merge with a larger continent, adding pieces to a giant jigsaw puzzle over millions of years.
A geological jigsaw puzzle. Love it.
And don't forget simple sedimentation. Over long timescales, erosion wears down mountains, rivers carry that sediment to the edges of continents, and it builds up, eventually turned back into rock. That adds volume too.
Wow. So it's a really dynamic, multifaceted construction process over immense timescales. Subduction, scraping, collisions, sedimentation.
Absolutely. And one more point from the notes, that partial melting bit.
Right. Partial melting of the oceanic crust at subduction zones. How does that add to continental crust?
Well, when the subducting oceanic crust itself starts to melt under heat and pressure, it's the lighter, more silica-rich components, the more felsic stuff, that tends to melt first.
Okay.
This felsic magma is buoyant, so it rises and adds itself to the overlying continental crust, making the continent even more felsic and distinct from the denser oceanic plate it came from. It's another differentiation process.
Got it. It reinforces that felsic character. Okay, we've covered a lot. Thickness, composition, density, age, formation. Now, the notes also mention seismic wave velocities. This sounds a bit more technical. Why is this important? What do seismic waves tell us?
Seismic waves. They're basically vibrations, energy traveling through the earth, usually from earthquakes or artificial sources like explosions.
And S waves, right?
Exactly. P waves are primary or compressional waves. S waves are secondary or shear waves. And the key thing is they travel at different speeds depending on the material they pass through, its density, its rigidity, stuff like that.
So by measuring those speeds,
By measuring how long it takes for these waves to travel from a source to seismometers around the world, scientists can build up a picture of the Earth's interior structure, including the crust. It's like doing an ultrasound or a CT scan of the planet.
a CT scan of the Earth. Okay, that makes sense. So what are the typical speeds in continental crust? Let's start with P waves.
Okay, P waves. In solid crustal rocks, they typically zip along at between 3.0 and 6.5 kilometers per second.
Per second, that's fast.
Very fast. Though in really loose stuff near the surface, like unconsolidated sediments, they slow right down, maybe 0.5 to 2.5 kilometers.
Okay. And an average for the whole crust.
The average P-wave velocity, VEEP, for the entire continental crust is estimated around 6.45 kilometers per second.
6.45 kilometers, right. And S waves. They're slower, you said.
Yep, S-waves are slower. They physically shake the rock side to side, and they can't travel through liquids at all, which is important deeper in the earth.
Huh?
In solid crustal rocks, S-wave speeds, Vs, range from about 1.5 to 3.8 kilometers per second.
Slower, but still pretty quick.
Stick quick. And again, they slow down a lot in soft sediments, maybe 0.1 to 0.8 kilometers. As a rough rule of thumb, S-wave velocity is often around 60% of the P-wave velocity in the same rock.
60%, okay. And the average S-wave speed?
The average Vs in the continental crust is generally thought to be somewhere around 3.5 to 4.0 kilometers per second.
So analyzing these different speeds, P and S, helps map out the different layers and rock types within the crust we can't see directly.
Precisely. It's a hugely powerful tool for understanding the structure and composition deep beneath our feet.
Okay. Now, there's one last point in the notes. Types of continental crust. But there aren't actually any details given here.
That's right. The notes just mentioned the category exists. And it's important to know the continental crust isn't just one monolithic thing.
It varies.
Oh, definitely. Geologists classify different types. There are, for example, ancient, very stable core regions called shields, or cratons, think parts of Canada, Siberia, Australia. They contain some of those oldest rocks.
Okay, shields.
Then you have younger areas like active mountain belts, the Himalayas, the Alps, where the crust is still being deformed. There are other classifications, too, based on age and geological history.
So different regions have different characteristics based on their past.
Exactly. It's a whole other layer of detail, definitely something listeners could explore further if they're interested in why, say, central Canada looks so different from the Andes.
Good point. Definitely food for thought for another time. So, okay, let's try and wrap this up. We've taken quite a journey beneath the surface today.
We really have.
We've seen how continental crust thickness varies massively, creating those huge mountain roots. We learned it's mainly felsic granite-like, that seichel idea, but with variations getting denser deeper down.
And that lower density is key.
Absolutely. The whole isostasy thing, making continents float high, then the incredible age rocks over 4 billion years old.
Mind-boggling, really.
And the complex way it forms and grows, subduction, accretion, those terrain collisions like a giant jigsaw.
A constantly evolving picture.
And finally, how we use seismic waves, those P and S waves, as a tool to actually probe that hidden structure.
It all fits together to give us a picture of this fundamental layer. Understanding continental crust really is, well, foundational to understanding Earth's structure, its history, how mountains form, where resources are. So much, really.
It really puts the ground we walk on in a whole new light.